So let's start with the basics of R. I know that Weimar had sent out an email with details about how to download R in R Studio. So R is one of the more advanced statistical programming languages out there. And a lot of jobs in the job market currently require R if you're doing data analysis or Python or some sort of statistical programming. And R and Python are great tools to begin with. So um, R right now is taught in one of our courses in industrial engineering in engineering analytics. So if you have ever taken that course, then you must be familiar with how to, use it and how to use it for modeling. If you're not familiar with that, we're going to cover some of the approaches in today's session. So please let me know if you have any questions in the comments or raise your hand. So R is a simple, intuitive, interpreted language, and it's mostly used for statistical computing. And any file that you want to save in R, you can save it with a .r at the end. Any file saved as a .r is an R file or an RStudio file. And similar to Python, and other programming languages, any lines written in a program or the editor, which is right here, which is called the text editor, is a part of the R statement. So if you write any line within this, it constitutes as a code except for a comment. So any comment, and all these are comments that you see here, start off with a hash symbol. And comments in R, the issue is that you cannot make multi-line comments, and you can only make single line comments. And that means anytime you write a bunch of lines, you have to comment them individually with hash. Or you could select the lines and just hit Control or Command Shift C, and it automatically comments all the lines that you have written down. So if you're familiar, if you've dabbled with programming, command lines are important to explain what the code does and give the reader or the user more information about what is happening within the lines of code. So we've used a significant amount of command lines in here. So when you're writing your code, we encourage you to do that as well. And moving on from the comment and little more about R. R is open source and it is free. So this helps it creates, sorry, it's very useful for students and other developers to use R to create functions and libraries. So if you're a young developer who's interested in programming, so R is a great way for you to start learning about it. So if you want to run any set of lines of code in R, you can just select them and hit Control or Command Enter, depending on your MacBook or your Windows. So once you hit it, it's going to run the lines of code on what this is called the console. And over here is your global environment, where you can see all the variables that you have probably run in earlier lines of code. And if you want to just delete this, you could just hit this and that should be gone. And any plots or any packages that you would like to download would be right here. So you could just pick them and install them on the left in your editor right here. So let's start with the basic. There's another way to run it. Run is select the lines of code and hit run right here. And that would also help you run lines of code within an RStudio. So R is the basic programming language, and RStudio is an interactive IDE. So it's very useful to have RStudio versus R because it is very functional, whereas RStudio is very user-friendly and gives you many ways to download data, to see what your plots are, whereas R is a much older version of this, and it's not as user-friendly as RStudio. So if you're only working with R, then I would encourage you to shift to RStudio. But if you're not comfortable with that, that's fine. Let's dig into the basic data types. So Within any programming language, we have types of data that we can use within the language. And similarly for R, we have certain types of data that we can use. And most of them are pretty straightforward. So the first one, we have numeric, which is any number. Other data types, we may have integer or float, but R is not complicated like that. Any number is called numeric. So I'm just going to run lines of code here, and you should be able to see the output in the console. So when I run n equals to 5, I'm assigning 5 as the number to the variable n. So when I run that, it automatically assigns. And there's another way to assign using this arrow. And this is one way to assign using an equal to. And these both are called the assignment operators in R. And once I hit that, I am automatically assigning the number to the variable. And class is an important function. It's a predefined function in R, and it tells us what is the data type of that variable. So n is a variable, and the class of n gives me the data type, which is n is a numeric variable. And when n is 0.33, there may be other programming languages that would call this float, but in R, we still call it numeric. And when n is -5, other data types may call it integer, but in R, it is still numeric. So if you reassign the variable, the same variable with different values, R would take the most recent value that you have assigned it and store it right here. So any variables that you run in globally, that is outside any functions, are stored right here, and you can take a look at them. Okay, and when you do assignment to a variable, the console doesn't display the value unless you actually call or print it. So if I just say n equals to -5, it doesn't print what n is. I'm going to have to actually just put n, and then it gives me a value right here. So when you just do assignment, it doesn't just do that. You have to actually call the variable, and this is an example of that. I am saying n equals to n times 3, and in the most recent value of n, we had -5. So n times 3 is now -15, and I am calling that to see what the value of n is. And to check again, the class of n is still numeric. The second data type is character, and anything between double quotes is considered a character, and anything longer than just one letter is a string. And within R, there is no differentiation between what a character is and what a string is. You can pretend like they're the same type of data types or objects and interact with them the same way. So when I just give that a single quote or a double quotes, it automatically considers it to be a data type of character. So here the class of n is character. And if I give it a longer name, and if I run the class of n, it is also a character. And the next data type is logical values or Boolean values, which is true or false. And this data type is very important when you're trying to consider any comparative operators. If something is greater than something, is it true? You could compare that and check using these kind of Boolean values. So here we have only two, which is true and false. And if you write it in any other way that is not this, if you write it as TRUE, it doesn't know what it is. It doesn't consider that to be Boolean. So make sure you have caps right here. And R is it is case sensitive. So if you all classes within R and all functions that are predefined and all keywords are case sensitive. Make sure that you remember what is the true way to write it. So if I write true as is, unless I put it within double quotes, this becomes a string, but this is not the Boolean value true. So let me just take that off. So n is true, and the class of n is logical. So the data type we have covered so far are numeric. We have also covered character, and this is logical. And same thing with false. We also have another data type, which is complex values. And if you have any imaginary numbers that you want to combine with your values, then you can use the, this is a keyword which which is equal to square root of -1. So you can use that just by, combining this. So n is equal to 4 plus 1i, and it's important that you put a numeric value right before I. Otherwise, it's not going to recognize I. I is going to become, it's going to become a variable. If you store something in I, it's going to add that to it. So unless you put a numeric value before this I, it is going to consider it a variable. If you put a numeric value, it becomes a complex number. So right here, the class of this variable is complex. But if I just run this without the numeric value, it says object I not found. If I assign I equals to 3 and then run it, since I have defined this as a variable, it identifies that, and n right now is 7 because 4 plus 3. But if I put 3i, the class becomes complex again. So we have some constants that are very useful in our programming, which is infinity, nan. So we use these when there are certain functions where we divide it with 0, which result in n. Which result in infinity. So 3 over 0 is actually undefined. It calls it INF. And -3 over 0 is also undefined, but this becomes negative INF. So that it helps us recognize what kind of the numerator is, what is the value of the denominator is always going to be 0. But you could identify using these two constants that the numerator is either positive or negative. And the next one is nan. When you're trying to define two values that don't, when you're trying to use functions or operators over two values that are not numeric, then it gives you a nan. So here we have an INF function, and we have another an INF constant and another INF constant. And the subtraction of those two values is not applicable. So nan gives you a constant that says nothing that it recognizes. So we have other constants in our, that is like pi e, where you can raise it to the power of something and find the value of e to the power, sorry, you can find the values of other exponents or the value of pi or other constants, and there's a list of constants for R. So you should definitely look into that and see what mathematical functions you would use to use these constants. So once we've moved on from the data types, we have data structures, and data structures are nothing but combinations of certain types of data. And in R, you have single class and multi-class data types, where in one class means that the combination of the data type should be the same. So any single class data structure, for example, a vector, means that every element within that data structure needs to be either numeric, or it needs to be character, or it needs to be logical. But you cannot have a combination of different types. But different classes of data structure mean that you can actually combine two different data types. So you could have a number and also a character. So let's start off with the single first. And one of the most important data structures you'll come across in R are vectors. And they're one-dimensional. You can create multi-dimensional vectors as well, but we'll deal with just one for now, and we'll move on to 2 dimensions afterwards. So the way to create a vector is you assign a variable, um, some name n. This is the assignment operator. You could replace it with an equal to as well. And C is the keyword you use for creating an array. So you say C of 1, 2, 3. So you could create C of 1, 2 as well. Sorry. And that would give you this as the output. And then if you add another number to the variable, it is going to change it to become a 1, 2, 3. And please note that every time you run a new variable, it is going to store that right here in the global environment. And you can go back to this or search for what variable you're looking for right here. So the class of n is numeric, and there are certain functions within R that help you verify whether what you're looking at is a certain correct type of data structure or not. So if I want to know if n, without even looking here, if it's a vector or not, then all I have to do is dot vector of n. And if it says true, that means yes, it is a vector, or it recognizes the data structure n as a vector within R. So even a single assignment, just n is equal to 5, the class of it is numeric, and it does consider it a vector. So if you just assign a single value, it also considers that as a single valued vector. If you want to give it more than one value, this is the syntax for that, and it will also consider that to be a vector. And thus far, we've been creating vectors that are numeric, and this is a character vector. The class of n is character, and it is a vector. So do notice that so far I'm only giving like type data for every component of the vector. So 1 is numeric, 2 is numeric, 3 is also numeric, and all these here are character types. So because it is a single class or one class data structure, we always want to give it the same data type when we provide it input. So this is a string typically, but considered character right here in R. So I'm creating it. Simply use the letter C, open bracket, since C is a function, and you put in your string or your characters, and it is still a single dimensional vector, and it is a vector, so it returns true as the value. So indexing or subsetting a vector or any other component of data structures is something very important. So indexing in R is actually much easier, I believe, than other languages, where you just have to call the number of the value that you want to index. So if I have assigned n as 1, 2, 3, now it's an array of 3 values. I want to get or retrieve the first value. I just use square brackets to perform any type of indexing in R, and just run this code, and it's going to give me the first value. If I run n as 6, calling the first element would return 6. And I can call multiple elements using the colon function right here. So within n, square brackets, and call any values between 2 and 5. So if I do that for the current data type, sorry. If I do that for the current data type, I only have values for 2 and 3, but nothing for 4 and 5. And because of that, it's going to give me NA. So this is an other constant, like NaN, which says not available right here. So this is a constant that appears when something doesn't exist. So as you see here, there is no value for the fourth and the fifth element, therefore it returns NA. But if I were to introduce them as 1 and 2, and if I run it, it is going to retrieve the second, third, fourth, and fifth element in the vector n. And we can also perform addition, where here we are adding a value of 2 to every element within the vector n. So our n was 2, 3, 4, 5. Sorry, it was not 2, 3, 4, 5. Our n was 6, 2, 3, 1, 2. And if we add 2 to every element in it, the resulting vector, and we're storing it back in n, So now n is modified to 84534. And you can perform multiplication in the same way. Let me just, print n before we do that. Yeah. So multiplication is the same way, and then division is also the same way. So since we multiplied by 2, dividing by 2 gives us this. If we divide it by 3, it gives us float values right here. But it's still considered numeric. So you want to remember that when you're working on operations with with R. So let's move on to two-dimensional values or data structures. And two-dimensional values right now, the ones that we are covering, are still single class. That means you can only have the same type of data type within all the values. So over here, n is a matrix. And this is the syntax for creating a matrix. You just say matrix, and then you provide it an array. And the way we create an array is the same way, it hasn't changed, which is C, and you give a set of values. So if you just do this and we give n, it is going to create it's going to create a single column with the number of rows that is equivalent to the number of elements of the vector that you have provided it. So over here we have 4 values, so it's going to give you 4 rows, and by default R is going to start filling values column-wise. So the class of n, it's a matrix and it is numeric, which is true. And let's start with something where we could create multiple rows. So here we are saying that we only want a single row. So it automatically calculates the number of columns based on the elements that you have provided. So, and it starts filling it column-wise. So it's going to go, so let's start with something more than this. So we said 1, 2, 3, 4, and the number of rows are 2. So we know that it's going to give us a 2 by 2 matrix. Since there's 4 values, the second dimension has to be 2. And we're asking it to fill by row. So we can say by row equals to true. And if we run this, we have a matrix that is starting to fill by row as opposed to starting to fill by columns. And if I don't have this and I run this, it's going to fill by columns. So, sorry, just a second. If you want to find out the functionality of any predefined function in R, you can just put a question mark and the function that is in question, or you want to know more about. And right here in the help section, it is going to give you all the information about it. So matrix is a function that creates a matrix for a given set of values. It will tell you what kind of inputs it takes, and it defines for our arguments in this case, since it is a function, and it defines what each of these argument is. And at the very end, it also gives you some use cases. So you could use this to run the code and see what it actually does. So this is some of the R documentation that you can find. So any function, say C, is also a way for you to find out more about this. So just put a question mark and the name of the function and run it, and you should be able to see right here in the help section. So going back to this, we know the class of n, it's a matrix. So once we have a data structure that is more than a vector, the class no longer becomes numeric, but instead it becomes the type of the data structure. So until now, when we were dealing with vectors, when we were doing this, it is a vector, we know that, and the class of the vector was a character, it was not a vector. But we can check if it was a vector using the is.vector function. But when you come to matrices, and you want to now find the class of the matrix, it becomes a matrix. So when you are working with data types or matrices within R, you want to, or when you're trying to combine them, you want to make sure that you have the same type of classes when you're working with. So I can combine two matrices, I can do that, but I may not be able to combine a matrix and a vector. So you want to make sure the class of the two objects that you're trying to combine is the same class. And this is one way for you to figure that out. And if it's a vector, the only way for you to know if it's a vector is using the is.vector and the variable that you want to check. And here I want to know if it's a character, so I'm just going to run this again. The class of n is a matrix, and it is a character matrix, so it returns true. So the way to subset matrices is very similar to the way we subset vectors in R, which we've done just a couple of minutes before. So if this is a matrix, an important function for matrices is identifying what the dimension is. So here, the dimension of my matrix is a 2 by 2. So let me just print it, and it is a 2 by 2. But if I say that's a single row, it is a 1 by 4. And by default, the notation for matrices universally has been, the row comes first and the column comes second. So the first is the row and the second is the column. We have one row and 4 columns, which is what we see right here. To subset a value or a matrix, we can use the brackets, the square brackets, and just get the value. So if we just want to identify a column or a row, so you just put n square brackets, just the first column, sorry, this is going to be the first row. So the first row and a comma, indicating that you want everything with every column within that row. And if you run this, you're going to get 1, 2, 3, 4. So I think this would work better with a 2 by 2 so you can see its functionality. So in a 2 by 2 matrix, you have 1 and 2 as the first row. So everything within the first row is given if you add 1 and a comma. And you can do the same thing for the column, but you change the direction of the comma. So for the column, you have n square bracket open, comma, 2. And if you want to identify a certain row and a certain column, then it's pretty intuitive. You just run the row and the column that you want to identify. So the second row and the second column is 4. And if that is what you put in, you get, it returns 4 as the output. So as you see, the way you index or subset function, vectors and arrays is pretty similar. And we will actually move to some type of vector manipulation. Let's take two vectors A and B right here, right? We could do multiplication to these two vectors, which is called elementwise multiplication, just by using the star function. And this is the operator to use for multiplying any two numbers as well. But what it does here is that it multiplies the first element to the first element of the second vector. So 1 times 4 is 4 and 2 times 5 is 10, and that is what it is trying to do. So when you want to perform matrix multiplication, then this is your operator, which is a percentile star percentile. And that results in the matrix multiplication of A and B. You can also perform transpose of a vector, where A is, 1, 2, 3, 4, and the transpose of A is right here. So when you're working with large, really large matrices, then you need to keep in mind that transpose is actually a computationally expensive function, and you want to make sure that you allow it enough time to transpose. So another thing we can do is add elements or combine two different elements within a matrix. So now I have 1, 2, 3, 4, and I have another vector B. and I'm creating A to become a matrix. So this was originally a vector, and this is another way to create matrices is you already create a vector and then you just pass that vector instead of C1234 right here, you can just pass the name of the vector that you want to transform to a matrix. And the result is right here. And if I want to combine the current value n, if I want to add two elements, which is 5 and 6, I could either combine it to the column or I could combine it to the row. And I can only do that because my column is two values right here, and so is my row. So if I have more than two values, then I need to change the size of the vector that I'm trying to combine. So cbind, adds another column to my existing matrix, and rbind adds another row right here at the bottom. So once I change this, I can find the dimensions of my newly bound matrix and using the dimension function. And as you see, I have 3 rows and 2 columns, so that existing 2 by 2 has now transformed to 3 by 2. Excuse me. There are other useful functions for matrices where you can find the inverse, which is also computationally expensive, determinant, and rank. So I would, suggest that you guys play around with this and, try to see what more you can do with matrices. And there are other ways to create matrices as well. So and manipulate those matrices. So try to create a larger matrix and try to find how you can find the inverses or the rank of such a matrix, and all the rules that mathematically apply also apply here. So if there is a condition that cannot help you find the inverse, or there's a condition where you cannot find the rank, all of those would also apply here. So make sure that you are applying the mathematical correct formulation to finding the inverses and the ranks. So for a two-dimensional value with different classes, so now we're moving on to different classes, and this is where you can combine more than one data type. Here we have A, which is a numeric, and B, which is a character, and we are creating what we call a data frame, and data frames are some of the most useful values. So all the values that you could manipulate, you can run for modeling, are data frames mostly, and you will find tons of data frames that are predefined in R that you could actually use to experiment with your R programming skills. So right now we're creating a data frame with a number and a character, and the only way one way to create it is using the function data.frame, and you just input or pass as arguments the two values that you want to combine, and you need to make sure that both are of the same length, otherwise it will not work. So I'm going to create a data frame n, and the view function opens a new window right here and shows us what the data frame looks like. And the name of the data frame is AB, which is just what we have provided as inputs right here. And the class of n is a data.frame or a data frame. So if the lengths are not same, like I said earlier, this is not going to work. So have taken a 5-letter number and 4-letter character vectors, and it is going to give you an error that say that they're both of different rows. So make sure that you have the same number of rows. And for the earlier data frame, you can find how many rows and columns are there within that using these functions. So the number of rows within a data frame is 5 for n, 1, 2, 3, 4, 5. And the number of columns are 2. And the dimension is going to be, it's going to act like a matrix, and it's going to give you the number of rows and columns. And this is also very useful. When you have a very large data set, you can identify the dimensions using this function. Now I'm going to create an example data set called students. This is another way for you to create a data frame. I'm going to just create a vector of names, a vector of numbers, and I'm going to call it the houses for each of this. And this is you can assign or change the name of your data frame using the names function. So once I do that and I view this, this is what it looks like. So this is another way to create a data frame, where you can directly assign the value or the name of the vector that you're assigning right here instead of doing it separately. So if you combine them, then you can have lesser lines of code, and it's going to give you the same output like I showed you right here. Now, subsetting a data frame is very useful and very simple. It's the same as matrices. Um, if you want to get the value of the first column, then you can just put the value of the name of the data frame and just square bracket and the number that you want to subset it with. And this is the first column. So it's going to give you all the names within the first column. And the same thing for the second one. It's going to give you all the names within the second column. And since we don't have anything with 0, it's going to give you data frame with 0 and columns and 6 rows. So this is just to show you that any unknown or unidentified columns cannot be called right here. And if you want to subset rows, you can just do it by the same way that we did for matrices. So right this way. And if you want to identify a certain value, you can just put 2, 2, which will give you the second column, the second row and the second column, which is second row and second column is right here, and it should give you the value 2. And the good thing about viewing data frames like this is you can actually use a filter to find any values or sort any values. So when you have a very large data frame, you can use the view function to identify some sets of variables within ranges or some things that start with a D or have D within them. So this is a very useful way to look at your data frames. So, and also remember that the view is case sensitive and the first letter is capital. Another way for you to subset data frames is using the $sign. And if you know the name of the column that you want to call, then you can do that. And it's going to give you the year column. And if you don't know what are the names of your columns, then all you need to do is run names and the value of your data frame. And it should give you right here all the names that are part of your data frame. And there are some more functions where we could use them to subset. You can play with them and figure out how you can actually use them to find values that are greater than a certain value within your entire data frame. So let me go over one of this. Over here, we're saying that the students $year. So we're calling the data frame students and we're calling the column year. And we want to find which of these values are greater than 2. So if you look here, and if you remove the filter, we know that 3 is the only one that is greater than 2, right, in the year column. So if we run this, it should give us the value of the row that satisfies our condition, or value of the vector. So right now, student.year is a vector. Let me just run that here so you can see what it looks like. And we're saying which of this value is actually greater than 2, and it's only the first one. That is why it has given us 1. If I create a data frame where this is 3 as well, and I'm going to run this, and let me run this. So since the first 2 values over here are greater than 2, it gives me 1 and 2. And this is actually a vector. So you can pretend it's a vector and you can subset it and use it like it is a vector. Now, if I want to find within my data frame the rows that satisfy this condition, all I need to do is students, and I'm going to give a condition which is going to result in a vector like we've seen earlier. And I want the rows that satisfy this. So I put the vector as the resulting rows and the comma and a blank space for the column because I want all the columns, and I just run this. So it gives me all the rows and all the columns that satisfy this condition. And these two are very important functions when you're working with data frames, when you want to identify what is, say, a certain value is equal to. You could even use equal to 2. Sorry. So there's only a single value that is equal to. So you could use less than 2, greater than, equal to, not equal to. So you can play with some of this functionality. And you can do the same thing with the character vector as well. Make sure that you're giving it the same case sensitive values that are fed into the data frame. And you can combine two of these values where the value of 1 is greater than 1, and also the house is equal to g. And you could use an or function here that could give you the either that satisfy the first condition or the second condition. And you can play with these conditions and see how you can manipulate data frames. So if you want to add a column to the data frame, you just create that column and you call the name of the data frame, and you open a square bracket, and this is the name that you want to add, and this is the actual function that you want to add. I could call it class and still add it, and it would, sorry, and it would add class. And I could say status as well, and it would still change it. So since I added, so it's not going to replace the existing function, but it's going to add new. So the number of times I keep doing this, unless it is repeating itself, it's going to keep adding. So I could change the name, and I could keep adding how many ever times possible. But if I keep the name the same, it is not going to keep adding to the existing data frame. So this kind of can cause confusion when you've added something, and you may still be assuming it works as the old data frame, but it doesn't. It has been modified. So make sure you're paying attention to that. So you can delete a column using this function. You can just call the data frame and the name of the column that you want to delete, and just say equal to null. And if I run this, it no longer has status as a column within its data frame. And we also have lists, which are very important data structures where you can combine different types of data types. So I have a number, I have a character, and I have a logical value here, and I have a vector, and I also have a matrix, which is a data structure. And I can actually combine all of them within my list right here. So your list is a combination of all the values that you provided as inputs. And the way you can access your lists are pretty straightforward. You can just, the same way to index matrix and data frame. But if you want to access something within your list, you will have to add additional brackets. So my list consists of 1, 2, 3, 4, 5 different types of elements within itself. So when I say my underscore list of 2, it gives me this. But if I say my underscore list of 2 of 1, oh, I may be wrong then. Yep. So within your list, I want to get the first element. So I'm saying take my first list and take my, so the way that lists are indexed, it shows you right here. So you want to call this, which is also an empty variable that just sits there, but you have to call it for you to be able to access the items within your list. And then I want to call the first element of my list. So right here. So if I want to do the same thing for the second one, that's how I do that. So the same way I can access other elements within the list, and you can play with them and try to see how you can access a matrix. If you look at the matrix right here, this is the fifth one, and then I'm sorry, someone is requesting control. I'm just going to deny that. It's the fifth one, so it is going to, you can just access the values within them using the square brackets. And my best advice to following subsetting or indexing is to follow the numeric square brackets that are already listed. Even in a vector, if you consider n, which is no longer vector, let's go with, if you consider n, you will right here, you will see that this is the numeric value. So this is nothing but the first value. And if you have a long enough vector and it goes beyond all this and comes to the second one, it's going to give you an actual number that corresponds to the first value right there. So if you follow the notation that is present here and use that to solve your indexing issues, then I think you will be, better guided using that. So assigning elements of a list to a new variable. So if this is the way that my first list is, and I cannot just add values to something to a list without actually calling them correctly. So right now, this is the way that I need to call them, which is what we were discussing earlier. So the first value is 1 right here. And unless I call it the way that the list is assigned, I cannot actually add anything. I cannot add a number to a list. And unless I call it in this manner, it is still considered a list. So this is, I can assign a part of a list to a variable called nums right here. And if you look at it, unless I subset it correctly, it is still considered to be a list. And because I cannot do any numerical operations to a list, it doesn't allow me to do this. So let us see how we are on time. So we have about 35 minutes. And we will have to cover converting objects, some type of operators, functions, and data sets. So let's go through that. Okay, so we have different types of operators in many languages. For mathematical operators within R, we have addition, subtraction, multiplication, division, and the modulus operator, which gives us the remainder. We also use this for matrix multiplication with a star in between. So matrix operators or matrix conversion operators of functions are different than just regular arithmetic operators. And you could just search them and find out what they are, like transpose of A or matrix multiplication, which is different than regular operations right here. Comparison operators are less than, greater than, they're pretty textbook operator values right here. And logical are and which, so we have something element-wise and vector-wise. So element-wise comparison is comparing each and every, so if you have a vector of 3 elements, element-wise compares the first vector to the first vector of the second element, second value of the first element to the second value of the second element. So which is the difference between the single percentile and the second ampersand, sorry, single ampersand and the second ampersand. And you want to play around with these to see what kind of comparison outputs or true or false outputs that you receive. So try to work on that offline. And some functions that are common to R that are predefined that are very useful are, we might have covered some of them already, like number of rows. So n row gives us the number of rows of a data frame. It does the same thing for a matrix as well. So the number of rows for this data frame are 6. And length is a value, is a function where you can find the length of a vector. So this is another way to initialize a vector where I'm saying it goes from 1 is to 20. And if you look at A, actually A goes from 1 to 20. And let me show you what I was telling earlier. So if you look at this, it goes up to 26 and it actually goes up to 200. But here it shows you the value of the index that is beginning. So 27, it starts with the index 27. You may have a different value here, but this is still begins with the 27th value. So looking at this, if you actually decrease or increase your the size of your console, you can actually easily identify how you want to index these values. So try to use this for indexing, which is very useful. So the length gives you the length of a vector, and for a data frame, the length will actually give you the number of columns. So if you actually want to find the dimensions of your data frame, use the dim function to do that. And this gives you the number of rows and the number of columns. So class is where you can find the type of structure or the data type, depending on what the object is. And over here, class gives you complex. For a single valued object, it actually gives you the data type. But if you're doing a multi-class or multi-dimensional object, then it's going to give you the name of the object or the name of the structure. So structure is also an important function, which actually very useful for data frames. And it gives you some kind of a structure actually gives you the kind of information that you see right here in your global environment. So whatever you see here is actually going to be printed as an output right here. So if I want structure of B, it's going to print the same thing that is here. So you can see some summary of what your data looks like. There are other functions that are, very useful, and we haven't used them, but you can try and work with them. And there are some, product, max, min, finding the range of a set of numbers, the mean, the median, and the variance. And they're very, straightforward. They do what they mean or what their names stand for. And if you don't know how to use something, all you need to do is just hit a question mark and the name of the function, and it is going to give you the documentation for that function, and you can learn how to use that. So if you create a vector A, right, and if you want to find the sum of that vector, you can use the sum function to do that. And then the product of that vector and the max of that vector. So these functions are pretty straightforward, and you can do that try using that for different lengths of vectors and see what happens. And other useful functions that actually generate values are norm, and there are other types of norm functions, but here norm actually generates a normal random variable, and it's actually a standardized normal variable, so it has 0 mean and 1 variance. So if I say norm of 5, it gives me 5 values with that are part of a normal distribution with 0 mean and 1 variance. So there are other functions that do that as well, which is exponential. You can generate gamma function, gamma distribution, and binomial distribution. And each of these have, you can generate distributions of different types of lengths. And you can actually generate distributions within a range. You can say that I want norm or gamma between 0 and 1, then it actually does that as well. So use the R documentation and the question mark function to identify how to do that as well. So rounding off a value is round of A. So let's just go A, that's A, and round of A rounds every value within it. So the round is pretty straightforward, 0.5 higher, it goes up to 1, and less than 0.5, it rounds down. You can actually round to the nearest decimal place. So here I'm rounding up to the nearest 2-digit decimal places, and that is what it does right here. And we have a repeat. So this creates a repetitive pattern. So if I just have 2 values, the first value is repeated with the second value's number of times. And if I have a vector, the first vector is repeated, just the vector is repeated the number of times that you input. So this is also pretty useful function, so you don't have to sit and create long lengths of vectors if you want to work with. And this is sequence where it generates a value within the range of the first and the second number. And this is the gap or the increment that it is going to create within those two values. And we've already seen how 1:10, so this function works, right? And then we also have append, where we can add a value to the end of it. If you look here, 3 was actually an integer, but when you added it to a vector of float values, it converted 3 to a vector, a floating value. So this kind of conversion is called coercion, and R uses a lot of it. So if you think that you're still working with an integer, remember that there are certain rules within R that transform the value based on what operation you performed on it. So make sure that, for example, if you add an integer and a float, the result will be a float. It will not be an integer. So if you're still thinking it's going to be an integer, then you may be in for a shock. So you can append values, and you can also concatenate two vectors. So concatenating is just merging two vectors, and it retains the original value. So if it's an integer, it retains the value of the integer versus append. So they both serve different functions. So make sure you know how to use them or differentiate between both of them when you want to use them. So table actually gives you a frequency of a bunch of numbers, and it's very useful when you're working with data frames and you want to get some statistics. So I've given a bunch of numbers, and the table of B is a function that actually tells me how many times a certain number repeats itself, or the frequency of the values within the vector. And sample is a way where you could get random values of a certain amount of number. So I want to sample 3 values within the vector B, and sample of B gives me just that. And every time I run it, it gives me some random value. And cum sum gives us the cumulative sum. So for every element, so it adds the first value to the second, and then the second value to the third, and by the end it should add all the elements up until the last value. And cumprod gives me the cumulative product. And like I said, if you don't understand what some functions do, you could use the question mark to identify the documentation for that function. And finally, we move to installing packages within R. If you want to install any package, and every package is useful for different functionality. We have certain packages for plotting and visualization, certain packages that we need for regression or modeling. So you want to install the package with the name right here. Okay. So if you see here, there is a small stop button that comes up. That actually means that your code is running. So up until now, the lines of code we've been running were so small that you could barely see it. But once the code takes a bit longer, installing packages takes like a bit, like a second sometimes. So it shows you that something is actually running. So if you want to stop the code from running, or if you've written a code that is way too long and you want to, stop it, and you want to check something, you can actually hit the stop button. So unless you hit the stop button, you cannot run any more lines of code. So you have to actually abort the procedure that it's running to, progress any further. Excuse me. I'm so sorry. So there's another way sometimes to install packages, and that is just by, actually this is a way to call packages. Once to install them, you can go to the packages tab right here and just hit the package that you want to use. And you can actually search for packages within here. I could want to use dplyr, which is a very useful package, and it just attaches it to the library. So anything you have installed in your computer, it has that list right here. And some packages, when you install RStudio, they come automatically, so they already are here. So if something doesn't exist here, then you can actually use this function install.package to download it. And then to call it, which is when you want to use it, you can just either click on it, or you could just, call it right here. Now let's go to user-defined functions, and we have some functions that we've been working with so far. Install.packages is a function, sum is a function. These are all predefined by R, and user-defined functions are important when we want to create our own sort of functionality within R. And this is a syntax for creating it. This is a pretty straightforward syntax, and most, programs have the similar setup, programming languages. This is the name of the function. This is the syntax where you call the function. And these are, within these brackets, you're going to pass the arguments of the function. Here, this is the body of the function where you do some kind of calculation, and this is the value that you're going to return. So if I want to do this, I'm just going to run that. And I am actually creating a vector, and I'm passing the vector as a argument to the function, and it gives me 6. And here we're just creating a function to find the value of a vector. So this is nothing but the total product of a sum of a vector. And we already have a function sum that does that, but we've just, created a user-defined function right here. You can have functions within functions. So you could create a function, not sum, and use it within this function as well. So functions are very important, especially if you're, doing complex coding. It is good to summarize your acts within a bunch of code, and, call them when you need them, especially if you're going to keep repeatedly doing or calling something. So make sure to work a bit with functions when you're generating code for R. And now we are going to work with or look at some of the data sets that are inbuilt within R. And within right here, we have 2 data sets that are already sitting within our directory. So what we want, before we even go there, we can actually load data sets into R, but let's see what we have internally. So if you call the data function, we have a set of data sets or data frames or even sets that exist within R, and you can use any of them, call any of them in this manner, just with the name right here, and call them to, work with them. So I'm calling US arrests, and if I want to view it, this is what it looks like. So this is the state and the number of arrests that happened for murder and assault and the population. And this is the number of arrests for rape. And we could use the head function to get the first, I think, 6 to 7 values of the data frame. And we can actually use the tail function to do the same thing from the bottom part. So the tail gives you the last 6 to 7 values within the data frame. And the structure of the data frame gives you, every row, or sorry, every column and what they actually look like as a numeric. So if you notice here, it actually differentiates between a number and an integer. But as a data frame, as a data type, it doesn't. So this is just for our reference. So make sure that you don't see that there's a new type right there. And you can actually, to begin using them, you want to use the function attach right here. And then you could just call the functions as if you don't have to write US arrest $murder. Instead, you could just use murder directly if you use the function attach. Otherwise, you'll have to call it in this manner. This is how we call a column in a data frame. So if you want to read a data frame that you have created, which is in a CSV or text file right here, there are two ways to do that. First, you want to get the working directory. So right now, I am, all this is stored in my desktop in a folder called Bootcamp, right? But my working directory right now, I'm just working in users / my last name. So you want to set the same working directory as the data that you are currently in. So um, you don't have to, but it is best to have the data and the code in the same folder in your computer. So the the current working directory is right here, but I actually want to change it to Bootcamp. So I'm going to change it to space R. Okay, this is much longer. So what I'm going to just do is I'm going to put this here. No. So what I did, yeah. So because I changed the location of the file, it's not going to give me that. But what you could do is once you save it and then you put it out, and then I can reopen it. Right there. And now if I get the working directory, it's still working on users and Tatapuri. So I want to set it to the working directory that I'm working in. So right now I'm working on my desktop in a folder called Bootcamp. So I'm going to, okay. So if I'm not sure why it's not working as a function, but there's another way for me to do that. So I can go to session and I can set my working directory to whichever there. So right now I've set my working directory to, because I know why. There is no, this is not. Okay, so the way you work, the working directory for MacBooks and the working directory for Windows is different. So this is a Windows working directory. That is why it was not working. So the workbook that I'm currently working in, I can set it using session, right? And I can choose whichever directory, and it would do the same thing as this. And if you know what your directory is, I could, just copy this, and it would do the same thing. So right now I've set my working directory as this folder right here. Okay. And I have two data sets, which is train.csv and train2.txt. And I can run them both right here. I just need to call them read.csv. So I'm sorry for the confusion. So what I'm trying to do right now is that I'm trying to read the data sets that I have created in my folder. So we have just saw that there are existing data sets that we can use. This is ways to load data sets that already exist within your computer. And you use read.csv function for that. And my data, this is what it looks like. I can view it. Right here. So these are the values or the data that are stored in my computer that I was just loading. And for a txt file, we could use a read.table, which does the same thing, but for txt. There's actually other ways for you to do it. You can actually import from text file right here. You can also do that. So there are multiple ways for you to load data sets, and I've shown you two, and they're pretty effective. I actually just import my data set right here, so I can actually remove columns, or for example, if I want to open a CSV file, the kind of separator I'm using is a comma because it's comma separated values. And I could choose to have heading or not have heading right here. And if I import this, it executes this line of code, which is very similar to what we ran right here. So just keep in mind that it actually gives you the code for which, even if you're doing it within the IDE itself. So moving on to the loops, we have for, while, and if loop, and the functionality of these loops are pretty straightforward. It iterates between the values for while, it performs the function till it breaks the loop, till the condition is not satisfied and breaks the loop. And if is a comparative operator, and you can use it to print to perform different functions within R. So we also have if else, and there are some more functions, and they're pretty straightforward, and they're very common to all programming languages. There is nothing more complex with here. The only thing that would be different is the syntax. Some may have colon. R does not have colon. R does not care about indentation as much as the others. So if I run this with an indent, it still runs, but Python would not give me the same, it would give me errors if I have the wrong indentation. So for that, R is much more user friendly and lesser things to worry about. Lastly, let's cover visualization. So R is really good at creating visualization. The ones that I'm showing here are pretty basic, but you should explore the various packages that R has for creating plots. So right now I'm just creating a list of 1:10. Sorry. Yeah. And I'm creating a scatter plot with the values. I'm creating a normal generating normal variables with the 0 mean and 1 variance. I want 40 of those, and I'm just creating a scatter plot with respect to the data that I have just created. So I've created one called time, which goes from 1 to 40, and the other called price. And I've just generated normal random variables for that. And this is what it looks like. And this is the scatter plot for that. You can also create histograms using, I'm using a Poisson function to create 10,000 variables and plotting the histogram for that. I can also develop bar plots within R, and you can do box plot, you can do scatter matrices, you can do correlation matrices between two variables. And the code for doing that is pretty straightforward, unless you want to include more complexities and more visualization for for your data. So those pretty much cover some basics for R. And I'm quickly going to go over tree function over here. So we have, moving on from data. So once we have data, we want to use this data to create some kind of informed decision making. And trees are one method to do that. Excuse me, sorry. So trees are one method to actually create decision making using the data that we have. And what I'm specifically talking to is about what we call a decision tree model. So it's a modeling approach where use we have data, and we have a response variable, something that is the outcome, or an dependent variable, which is an outcome of several independent variables. So the price of a house may be the outcome of the zip code. It may be the outcome of the number of bedrooms. It may be the outcome of the number of bathrooms. So the price is the response variable, and the independent variables are the zip code, the bathrooms, and the bedrooms. So I can choose any of these independent variables to make some decisions about my dependent variable. So I can use the number of bathrooms or bedrooms within my house, I can use that factor to determine what the price is going to be. So one common way to do that is regression. But when you work with more complex data structures that have, hidden features that you want to identify, one other way to do that is using trees. And with trees, you can do both. If you're not already familiar with this term, classification or regression type of trees. So classification is, identifying a category. So maybe whether this house is going to be sold or not. And regression would be to identify a quantity, which is to identify if this house, what the price of this house would be. So to building a decision tree for you to help make that decision is what we would really need is we would want to know what feature to split something on and when to actually stop splitting on. And what I mean by split is that we want to start actually, you know what we mean by split? Once we see some pictures or images of the outcome of the decision tree, maybe we'll understand better. But first, we want to pick a feature which we would begin the split on. So if we consider price as the outcome, and we have three inputs, which is what I said before, which is the zip code and the zip code and the number of bedrooms and bathrooms. So those are the three inputs of the. We want to decide which of this input is the most important for us to start making the decision on. And that is the feature which we will begin splitting on. So, and our goal is to select a feature that will produce the most homogeneous results. And we don't know just by looking at the data which feature is going to do that. So what we actually do is we either calculate something called entropy or information gain. So either of these values help us determine which feature is really good to begin the split on. So entropy is a measure of the randomness within a data set, and we want to minimize that, or we want to maximize the amount of information we gain. So it doesn't matter which one you pick, entropy or information gain. Either ways, we could use one of these values to make the decision on. So let's move forward and let's start with the tree. So the data that we have is this is the data, and it's just the age, the number, and the start. And we want to see the summary of the data right here. For each age, number, and start for each factor, it gives us the summary. And and using the names function, we can find the column values of each of the columns within the data frame. So for this data right here, we see that this one right here, this is our response variable. So the kyphosis, it depends on three independent variables, which is age, number, and start. And as you can see, this is a categorical variable. So the kind of decision tree model we will be building is a classification decision tree. So when we want to begin growing the tree, we use the rpart function. This is the response variable. We say that we want to find the response variable and how it is dependent on all the three values. So we say age plus number plus start. And then we want to say that this is a classification method. And the data is the name of the data frame that we are just looking at. And since we are providing the name of the data frame, we could just use the name of the columns here, and we don't have to say data $kyphosis here to find that. So once I run this, it is beginning to grow the tree. And what we can do is, before we even go into here, so we can, if you're familiar with, tree building, then these are some, ways for you to understand the parameters of it. So we have something called the complexity parameter, and we use it to control the size of the tree. So if you plot the complexity parameter, which is something that, modelers use to identify the sizes, you see what is the relative error depending on the size of your tree. So if your tree is small, then you have a very large error. The bigger the tree gets, the error decreases. But the bigger the tree gets, it also gets more complicated for your model. So you want to try to see which model gives you the simplest tree while also retaining sufficient error as well. So I fit the model right here, and here is a summary of all the things that I fit. So it has created a comprehensive summary at the end right here, and you can actually go over that if you're familiar with decision trees and see which of this makes useful information or more sense to you. And it gives you some type of splits that it generates. It says that it could start splitting with the start, and it could start splitting with less than or greater than 8.5, and then it could go over to number and split less than or greater than 5.5, and then it could go over to age. So because of this, what it does is it creates different types of splits, and you can actually plot the tree right here and then add the text. So it does several observations and it gives you the tree that gives you the best results. And it says it starts with start, and any start greater than 8 equals to 0.5. So the outcome right here, which is absent or present, you're trying to see what values gives you that outcome. So if you go with the start value of greater than 8.5, which likelihood that the start column gives you the most entropy, sorry, the least entropy or the most information gain. So it began with that. And it says that, okay, if I start with start and if start is greater than 8.5, then it's a very high likelihood that it will be present. So if you go look at the data, if the start is greater than 8.5, the likelihood of it being present is 8 over 11. So if you see, there are many values where start is greater than 8 and the outcome is present. And if it is less than that, then you still need more information. So it's going to go with start greater than equal to 14.5. And then it's going to split on age. And then it needs more information, so it's going to split on age further. So if you follow this trend, you will see that many of the values that you follow, that you make these decisions, would likely be similar to the data that you see. So this is one way for you to make decision making using trees. And this is a very small example, so don't see that it may not be really good quality example for the data that we have, but the better data you have, you can build better trees. So when you have more complex data, you fit the tree, but you have to also start to prune it. So this is a way for you to, reduce the size of the tree. And once you prune the tree, I'm sorry. Okay. I am not quite sure what this, it should actually cut off either a root or a branch of this tree to prune it. So I'm not sure why I'm not able to do that. But um, you should definitely, look at how you can prune a tree other than the mentioned method right here. So let's move on to a regression example. And right now we were doing classification, and we're using a different data for regression. So a regression also does the same thing, right? It creates a tree, and the only difference between, I'm sorry, I'm moving faster, but the only difference between regression is it doesn't give you whether it's absent or present. It's not a categorical. Instead, it gives you a number right here. So you can, again, okay, that's good. See the pruned. So a pruned tree is what you see right here, but it hasn't actually pruned anything. So that means that it probably doesn't require much pruning, and it's a small one to begin with. Pruning is based on your complexity parameter. So it modifies the pruning based on that. So you have to change the complexity parameter for you to, perform some type of pruning. And we're finished with tree-based modeling, and right now we are going to linear models or linear regression models. And let me so this is the data that we will be using for the regression model right here, which is a linear regression. And we're right now just preparing the data for providing it as input to this function. And here we have GLM. And MEDV is the response variable that you want to fit the model to. And by saying, by using these two symbols, we're saying let's use it for all the variables within them. So earlier we were only using 3 variables, which is age, number, start. But if I just did dot, it would just use all the factors of the data. So that is what we're doing here as well. And so if I, some things to know before you perform a regression function is, you want to scale your data set. You want to know whether there's any NAs and you want to remove them. You want to replace them either with the mean or the sum of the columns of the data frame. The mean or the average values of the data frame. So once you perform the modeling of that, you want to use that to fit the model to the values you want. So we are using it to fit it to the response MEDV to all the values. So these are the number of rows within these are the number of columns of the data frame, and everything has a certain, value. And this gives you whether these values are significant or not. And as you can see that there's a lot of values or a lot of columns or factors that are very important. And you want to remove factors that are not important and maybe run this again. So one way to check how good your model is through mean square error. And this is one way to see how efficient your model is. So you can compare two regression models using its mean square error. And the idea is to try to keep the mean square error as low as possible. So you want to pick a model that gives you the least error. And we have another fitted network, which is called the neural network. And I am going to actually quickly go over this. So neural networks have become, a very common household name for programming, and we can use the neural network to identify the outcome or the combinations of inputs to the output. So if you want to find, we can use a regression, but it is not going to be a linear value. We are going to use something, we are going to introduce some complexity within our data and find the outcome of that. And that is what a neural network does in general. It has a structure that has layers and nodes within itself, and that is different than regression. So what we're going to use is we're going to use a library called neural net. And let's just quickly, sorry. So we're going to use a library called neural net, and it's the same data set that we've been using before. And this is a way to just formulate our data structure or that we're passing into the neural network. And this is a way for us to create the neural net. This is our function to use the neural network. And we're using the data structure that we have here, and we're using some set of, so let's look at F before we actually. So this combination gives us that we're saying that the data structures we want to use or the factors that we want to use are these. These are the independent variables, and this is the outcome right here. And we want to use some set of data for training alone, and we have already created that data earlier. And we want to use um, some set of hidden nodes and layers, and we are giving the number right here. And the kind of function that we're expecting is a linear function, which is a combination of the nodes and layers, which is a linear combination. And we're saying that the linear output we want is true. So that is what we have here. And we just plot the way that the neural network activates and all the rows that it considers right here. So I would, request you guys to go over some of this methodology since we are a little short of time and see how we can use it. I think I'm gonna take my leave here. Oh, I'm sorry. I think Waymar can maybe cover this more if you guys need it. So I'm gonna leave the rest to him.
Thank you, Hanisha.